Hello! This is Group 1's Uniform Stress Cutter project. Our group is comprised of Melvin Mathers, Scheffer, and Leah Winkelman. And this is part 2. So, where we left off in the other presentation was we looked at many existing tools to base our designs on, like golf ball cutters and egg toppers and paper cutters, and we analyzed their effectiveness at being a universal stress cutter, how evenly they were able to cut, and how useful they would be when cutting a cylindrical object. We also 3D printed a sample cigar cutter to test after determining cigar cutters would be our best option to base our design off of. And then from there, we identified goals for a prototype and started designing. Over here on the side, we could see up top we have a past idea of a uniform stress cutter. This was a very early on sketch. It was based mostly off of a golf ball cutter, and it has a singular blade and a tray to cut down onto. It worked kind of like scissors, where as you press down, it would cut. And we quickly scrapped this because it cut starting from the center closest to the axis where it would move, and then it would apply pressure from that outwards, and that was just not going to work for a universal stress cutter. From then, we looked at paper cutters, and we looked at two kinds. We looked at a flat one that only works with like thin sheets of paper, which would not work for our project since we were doing a cylindrical object. And then we looked at a larger one, but it had the same issue of only applying pressure onto smaller spaces at a time. So, what else did we look at? What we did not draw from right off the bat was a box cutter or a singular blade design, because that would only come in for one point. It would cut a very tiny point, and they were kind of hard to handle. You'd have to have something to clamp down the item onto in order to get it to cut in one spot consistently. What also is included in there is a rotary blade. A rotary blade cuts as you roll it across, but it only cuts in one small section at a time. It is even for fabrics, but not for cylindrical objects, which is what we're working with. And we didn't look at any like laser cutters or any machines that had a lot of intricate electrical work, because we are only a group of 3 for a few months, so we figured that we would not have enough time to get anything working with that, and we'd stick with a purely handheld, non-electrical device. So, our previous example, and what we did a lot of testing and a lot of brainstorming with, was a handheld cigar cutter. The pros were the fact that it was handheld, but that's what we were aiming for, something where you can just hold it and put your cylindrical object through it, and it would create the cuts. And like I said, it cuts cylindrical shaped materials, so it was a good start for figuring out how to cut our objects. The cons were it does not apply pressure evenly. There was only a singular blade that was in it that would cut across the hole over here, and it would come from one section. So while it was handheld and easy to use, it didn't work exactly how we were hoping. So from there, we were coming up with designs and ideas of other things that might have more blades. An issue with this as well was that the body was made of weak PLA and very thin structures, so as we were testing it, it broke. So our goals were to make something stronger with more blades. When brainstorming that, we happened to find the 3-blade cigar cutter, and with this, it was very similar with the other one, handheld, and it cuts cylindrical shaped materials just like the other one did, but it has 3 blades coming in at the same time as you closed it like the scissors, and closed the handles together, which would better evenly distribute force. And this was exactly what we were looking to do. And the cons were with this, there was only 3 blades. If we had the ability to add more blades, we can make the force even more evenly distributed. And this was the closest we got to what we want our prototype to look like. Another thing we wanted to add to it as well was there's no way to measure how far in the blades came when it snipped off, because you're supposed to do it in one smooth movement of closing the scissors and cutting off the tip of the cigar. So what we wanted to do was create it so we can adjust a little bit at a time and really see where the material breaks off. So, our first prototype we displayed at the end of our last presentation was where we started from there. The pros were it cut the cylindrical shaped materials, and how it works was as you turned the handle, it would have a mechanism to have 4 blades come in. And with those 4 blades, it would hopefully cut it easier, and you're able to do a little bit at a time with moving the handle around, so you can see really where it cuts off the material. This would add a lot more evenly distributed pressure from the last ones we've seen because it ups the blade count. But the issue is we had a lot of difficulties when trying to manufacture this. From trying to print it out based off of what we 3D modeled, to trying to create mock-ups, to figure out where we were going wrong. It just was really difficult to work with. Another issue is since it would cut in the hole in the center and we had the bigger piece there to rotate, it would only cut very thin pieces off of that cylindrical object. So overall, we knew there was a lot of room for improvement, so we decided to fix that. So our future plans going forward from this prototype were take what we learned and make a design based off of these ideas and aim to the best of our ability to create a sturdy final product so that we could actually test it and see that it works. So this is the prototype that we started this half of the semester with. It's a very simple design since we were trying to keep it easy to manufacture and prototype, although we did run into many difficulties with that. But starting off our design was the circle on the top is a crank that as you turned it, the blades, which are attached to the arm that you see there, would turn and move in. The black square part of it is the housing for the blades, and this we made out of a plastic because it doesn't need to be crazy strong, and the housing just keeps the blades from touching you, and the center part there is where you would enter the material. So we were also struggling with the difficulty of trying to find clearance, since you could only cut like maybe a centimeter off of each material. So that was part of our struggles here, especially since with the hand crank and everything, we were struggling to be able to hollow it out and still have it work just fine. As I was saying before, a lot of this we were changing and just having a base design so we could build off of that and start our prototyping, but none of it was really fleshed out, so we don't really have any pictures to show you guys. But with this, the arm was way longer than it needed to be just so you could easily see how the mechanism was supposed to work. The arm would have a plastic piece that hold the blades in place. There would be 4 of them attached to the crank. So as you turned the top part bit by bit, each of the 4 would slowly make their way in and better uniformly cut the material. While the arm would be shortened, so would the edges of the square. It could be rounded off into a circle to be easier to hold and easier to use, nicer to look at. But with this, we were really just getting a rough idea out. That's exactly what this prototype was, and we used it a bit for inspiration going on to our next portion of the project, but it kind of was its own thing where we could live and learn and figure out where we were going from there and the prototyping process. And that is exactly how we moved on to our next prototype, which we'll show you in a second. At the time we were working with this idea and believing this would be our final project and final part of the project, we discussed the materials we would make everything out of. The black portion would be a thinner, not too thin, but like a plastic, since it didn't need to be very strong, since the only reason it was there was to prevent you from cutting your fingers and like getting injured. The crank and the portion holding the metal blade, however, we were aiming for a stronger plastic and even debating ideas of reinforced carbon fiber to try and make it as strong as possible with the materials we had, since we do have access to carbon fiber filament. But the goal was to have a 4-blade cutter, and we ended up moving on to a better design that even fit into 5 blades, and I'll head on right over to that. and not break as easily as the cigar cutter did. So our timeline we came up with after the last video was week 4, we were going to continue designing that prototype and tweaking it. Week 5, we were going to manufacture our final prototype. And from week 6, we were going to test and refine the final prototype and make sure it works. But, as per all projects, it didn't go to plan. For week 4, we were finishing up the designs of that prototype I just displayed, and it just would not work. We just could not get it manufactured. We tried our hardest to produce it, even like physically, like I said, with cardboard, with whatever we had, and we could not get it to stay. So towards the end of week 4, we really had to start developing our new prototype. And that lasted going into week 5. Week 5, we had our new prototype that we were working on, and we only started manufacturing towards the end of week 5 into week 6. So as we reached week 6, that's when we were really finishing up that design and manufacturing and making sure it worked. So our final design is this gear mechanism, which allows all blades to protract and retract simultaneously along the tracks shown. They all go in and out, and with the gear mechanisms, it'll be as you're turning it with your hand, and there's the hole in the center where the cylindrical object would go to be cut. All the gears allowed for very minute movements where we could really measure exactly how far in the blades have gone before it's cut the object. And as you can tell from the other ones, we've upped the blade count. It's got a 5-blade design rather than a 4-blade or 3-blade or 1-blade. So we're really trying our best to have the best final design we can. And this, especially compared to the last prototype, very easy to manufacture and assemble. We were able to get this done in time. Here we will be showing our final design and how we designed it in CAD, starting off with the base of the product. Right here you see where we start to add the tracks and the mechanisms to make the blades go inward. And you'll see, as we're designing it, we find out how to make it visible and workable on CAD as well. As with all CADing, what you'll see here is it takes a lot of trial and error to get it to work out perfect. Right here you'll see is where we try and get the gear working on there, showing how we turn the mechanism with our final product. And here is where we start adding in stuff for a hand crank so we can easily adjust and see how far the blades go in for this product. Here is where we're adding in a second gear to get the hand crank to work. The gear is attached to the hand crank, so that leaves only 2 gears in this whole process, and it makes it a fairly simple product to manufacture.
Alright, so what we have in front of us today is our disassembled but completed final design, for now. What we have here are these slots, these are our dummy blades for safety reasons as well as school rules. These blades here slide in these channels. They have a peg on the back of them, which you can see on any of them here. This peg holds them in the channel so they can slide back and forth like so. And as you can see, when they're all the way back here, the dummy blade is not in contact with the hole whatsoever. when they slide in like this, they are in contact with the hole, so they can cut something of this rough diameter. These blades can be exchanged for any length blades depending on the need of the material being cut. But they slide through these channels in and out via this gear right here. This gear, this black gear right here, works with this pink one on the side here, and it rotates itself around so that when there is a pink dummy blade, or a real blade ideally, in the slot, you move it like this and it slides it through the slot, which I could demonstrate by putting in a pink dummy blade. So you can see it's in the slot right here, it's all the way at the back, and then I rotate this like this and it's out. So this, you can see the gear kind of comes unaligned towards the back here, how it's way out here but not even touching here. This is because I don't have all the dummy blades in right now. This is just so I can demonstrate for you. But it's very easily disassembled as well in case you want to swap out these dummy blades. There are more covers for it that can be added, but for demonstration purposes they are not on here right now. The bolt right here is long right now. It can be used as the handle if you'd like. However, in the future we do plan on adding in the extra handle on the white. That way you can hold it and rotate it without getting your hand in the way. But when all 5 of these dummy blades are on here, they move with that gear. Putting the gear on is a bit of an alignment hassle sometimes after you change out these dummy blades for whichever new lengths or strengths you would like. That is also something we would look to edit in the future. But for right now, this is a pretty good uniform stress cutter design. So you can see here when they're all in a rough position, you can take your black gear and line it up roughly with the pink dummy blades, and then once all 5 of them line up, we've got 4 of them right now, once you can get the 5th one to line up,
A few moments later.
Now users may also find it easier to put the blades in after this black gear has already been set on it. However, it is all up to user preference. This black part also does not need to have the teeth all the way around. That does, however, make it a little bit easier when you're assembling it to line it up with the teeth up here, because it does not matter where this gear is rotated around. So I could set it on like this, or I could set it on over here, and it does not make a difference as to usability. Just a more generic lineup, but it's all up to user preference. If we were to make this producible, like I said, well, the same way you could interchange the dummy blades with real ones, obviously, you'd also be able to interchange this. Important note about this is the tolerances are very wide on the spots to fit those dummy blades, because the ones that would ideally be made out of metal would take up a little bit wider of a platform, and also it makes it easier for demonstration purposes for me to be able to take it apart and put it back together with these wider tolerances. But that is why you see a little bit of the jiggle when it is assembled. So this gear right here is just, it has a handle attached to it, this pink part here, so it can rotate around like this, and then you can do it with the handle. If this were to be produced out of the stronger materials that we would like to, then we will have measurements on here so you can see exactly how far you have to rotate this gear, or ideally how far these dummy blades or real blades in the real scenario have to go in before your material breaks. For a lot of materials that will just be the thickness of the material, but for some it might be sooner. Maybe it shears a little bit quicker depending on the material and its shear strength. So So that is the main idea behind us having the gear with the handle and the rotation, rather than just using two handles where you connect them yourself. This can give you a little bit more of a precise measurements.
Thank you for watching our video.